So here's a video lesson on week 2 notes, at least the things that will be a little bit tougher. So I will use an ALEKS to test this part. It asks you to convert into scientific notation. A little bit of hint here. This is actually an engineering notation. It would write out engineering, but I don't know how to spell it. And we're going to have to go back to that in a later lesson. So here we have 41 micro, so you have to have those prefixes memorized. We're trying to get to meters. So what is something that students sometimes struggle with is if you get 41 micrometers, this is simply the prefix that is associated with it. So there's not really a conversion that is needed here, as we could just write 41 times 10 to the negative 6. That negative 6 gets rid of that micro. We need, as mentioned in 1, we need the decimal to the right of the first non-zero. So I'm making that number smaller. I have to make this number bigger. So we're going from 4.1 or 41 to 4.1, and therefore times 10 to the negative 5th meters. So all of these are going to follow that same line of steps. So note, I won't be asking this ALEKS question because it just seems weird the way it asks it. So interconversion between of prefix SI units will not be asked. What will be one of the more difficult things for students to do is to convert things into engineering notation. The one thing you have to know for engineering notation is the powers of 3. And on slide 39, week 1, it shows you the powers that you need to memorize. Those include mega, which is 10 to the 6, kilo, which is 10 to the 3rd. Those are the only positive ones you need to know. Then we have milli, 10 to the negative 3rd, micro, 10 to the negative 6, and nano, 10 to the negative 9th. So if you are struggling with engineering notation, one thing you can do is write on the side the prefixes that can be used. Mega times 10 to the 6th, kilo times 10 to the 3rd, milli times 10 to the negative 3, micro times 10 to the negative 6, and nano times 10 to the negative 9th. So all prefixes need to be one of those. So let's just write a random number, let's say 5,200 meters. Let's convert that to engineering notation. So we can put a comma there to help us because commas go every third. So 1, 2, 3, we have 5.2 times 10 to the 3rd meters. Scientific note or significant figures remain the same, 2, and we can replace this times 10 to the 3rd with the correct prefix of kilometers. So if we added another 0, 1, 2, 3. Again, we have two significant figures. We can move that over. 52 times 10 to the third kilometers, if this is meters. And now we have 52, that's meters, and then we have 52 kilometers. So it's, again, about becoming comfortable with numbers. So let's go 5, 2, 0, 1, 0, 0, 0, 0, 0, 0, whatever. And we're going to put every third. This is not one you would need to do. So I'm going to cross over because the highest you're going to get is times 10 to the 6. So I'm going to work backwards to make sure I do that correctly. So here, we're moving the decimal. Now, if we moved it in front of that first 5 for scientific notation, then we don't have powers of 3. So essentially, entering those commas is a key, because this is going to be 55 times 10 to the 6. This is meters. And then we can replace that 10 to the 6 with megameters. If we added one more 0, 5, 5, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3. If we moved it any less than 6, or again, we're looking at these commas here, or however you want to do it, this is going to end up being 550 megameters. Same amount of significant figures for all of these. A -1 is, for example, the number is below 0 or below 1. So one thing I should have mentioned in the last slide, when doing engineering notation, the front number has to be between 1 and 999. So let's pick 0.001010, 0. So let's do one here. Since it's less than 1, I know that it has to be either milli, which is times 10 to the negative third, micro, which is times 10 to the negative 6, nano, which is times 10 to the negative 9th. We can use this comma way the other way as well. So 1, 2, 3, we could pretend there's a comma there. And keep in mind, again, we're going to either move the decimal 1, 2, 3 there, 1, 2, 3 there, 1, 2, 3 there. But if we did it any of those other ones, it wouldn't be between 1 and 999. So 1, 2, 3, 1.01 times 10 to the negative third meters. We can replace that times 10 to the negative third with milli, 1.01 millimeters. And significant figures remain the same. So there's essentially no rounding involved with these. So let's just pick, I'm just going to write 1. All right. So 1, 2, 3, 1, 2, 3, 1, 2, 3. So the comma that you want to go with is essentially after the first non-zero digit that's going to make that digit between 1 and 999. So here we have 1, 2, 3, 1, 2, 3, 1, 2, 3. That's moving that 9 times. So we have 150 times 10 to the negative 9th. I'm going to put a decimal there. So that is tricky. Let's say grams. And now we can replace that negative 9 with nano. So whenever I write these, I often think pico is negative 9, but then I remember, well, they both nano and 9 start with N. Therefore, 150 dot nanograms. And that's going to be as tricky as it gets because I had to add that decimal there, and negative 9 is the biggest number, or the smallest number, that you can get, and also there's 3 digits here. So generally speaking, that's as tricky as the question can be. Now, keep in mind here, how I'm going to test precision and accuracy is not with a dartboard, but more so with data. Accuracy and precision are different. Precision is closeness of measurements. Accuracy is closeness to the real value. Now, if I eliminate one of these, how can we make this student more accurate? We could have that student have a measurement of like 10.00 because the real value here is 10. So what would make the student be more accurate? We would put a number in like that. But what would it do? And think about this. What would it do to its precision? Also think about, well, if we have just one measurement, could we measure precision? Lastly, I might ask, if we don't have the real value, can we determine accuracy? So that's where I will go with this question. The density equation will be given to you, and generally speaking, I will use practice questions from Alex that you can practice at home to ask those. It is important, though, to remember 1.0 centimeter cubed equals 1.0 milliliters, and 1 gram of water is 1 milliliter and 1 cubic centimeter. So something like this might be asked. Something like this. All right. Now here we're going into moles, grams, all that stuff. This is a periodic table that I'll give you in the back of your test. You can rip it off and use it during the test. Now keep in mind the bottom number is the molar mass. So aluminum, if you were given 26.98 grams, and since you memorized the first 20, you know where aluminum is. You have 13, element 13. You have 1 mole of aluminum. This here, testable, so practice that. Again, here, testable, so practice that. This is not overly complicated, where we just have to distribute that 3 in and add up the masses. On Alex, you might have to, on the periodic table, I'll give you hydrogen's 1.01. On Alex, you might have to use 1.008 as sometimes they're just more specific with the periodic table that they have. They do have an ALEKS periodic table, which is sort of crazy because the 1.007943 or something like that for hydrogen. This is testable. So we're looking at these. We're going to go to the molar map. And knowing how to use that molar map is everything, or being able to comprehend the molar map in your head is important. So here, whenever you go from mass, which is going to be in grams, to moles, you're going to divide by molar mass. When you go from moles to number of compounds, atoms, or molecules, we multiply by this huge number, 6.02 times 10 to the 23rd. And that's because, so we mentioned earlier, that aluminum has a molar mass of 26.98. So if you had 26.98 grams of aluminum and you divided it by its molar mass, which is 26.98 grams, you're going to have 1 mole of aluminum. And in 1 mole, you have 6.02 times 10 to the 23rd atoms. So you would take that 1 mole, multiply by that number, and therefore, in your hand, that contains 26.98 grams of aluminum, you have 6.02 times 10 to the 23rd atoms of aluminum. So here, I might ask this slightly easier because it just sort of confuses us by saying there's a mass of a small airplane and 1 has a mass of this. However, if we multiply that number by 6.02 times 10 to the 23rd, we're going to get the molar mass of aluminum. What I want you to see from this, though, which I don't think I'm going to copy paste it out of Fluffin, or I won't. I'm going to reword this like, okay, so essentially aluminum, we have 5,000 kilograms. How many moles? And that's how I'm going to word it. This is, the way it's worded is just weird. It tricked me as well. So we have 5,000 kilograms. That means we have 5,000 times 10 to the 3rd grams, or 5 million grams of aluminum. 1 mole is 26.98 grams. So how many moles are in it? So you go from grams to moles, you multiply by molar mass. 6.98. And so we get 18532 moles. And we have 4 sig figs, so that's going to have to be 18530 moles. So I'm going to simplify the question, but doing these, Alex, is going to help you in the sense of how did I do this down here? I'm going to circle in green and get to that amount and then round it to that amount. Oh no, there's 3 sig figs there, so it'll be 18500 moles. So it'll help you get to the correct amount of sig figs. Now, I can't promise this is true all the time, but it's true all the time. This has 3 sig figs. This has 4. 6.022 has 4, so we're going to go with the least amount. There are elements that, when existing alone, bond with one another, and those are called diatomics, meaning two in atoms. So for example, if we said aluminum, it's going to be 1. But an example that you've heard throughout time is if someone goes O2, that's oxygen. So oxygen is a diatomic, aluminum is not. And the diatomics, there's 7 of them, and I'll take it to my grave that this is a backward 7. There's 7 of them, hydrogen, and then the backward 7, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So if someone says bromine and it exists alone and it's only that word, it's Br2. Iodine is I2. So it is those 7. So I think of a backward 7 kicking a soccer ball, and there's 7 of them, with hydrogen being H2. Some students go Brink, go Hoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, or something I still don't know it. Never fear having ice cold beer. Nitrogen, fluorine, hydrogen, iodine, chlorine, bromine. 1, 2, 3, 4, 5. So we're missing one. So I don't know. Come up with your own thingy. We're missing oxygen. So somewhere in that, I'm not getting it. Here, we have this many moles of bromine. How do we calculate mass? When you go from moles to mass, you multiply by molar mass. Now you can practice these on Alex, but bromine, remember, is a diatomic, and the bottom number on bromine is 79.90. So the molar mass for bromine is 159.80, because when you add numbers, you go to the least amount after the decimal, and you're going to multiply that by the amount of moles. Now, if this question gets asked for aluminum, which I don't know, could be a good question, then you know that it's just 1. So bromine looks like this. When we get to it, aluminum looks like this. Because bromine has 2, aluminum has just 1. Therefore, you would not multiply by 2 or add them together. We see that here. We have moles of magnesium oxide. We have to find the molar mass of magnesium oxide to go from moles to grams. You multiply by molar mass. You have 2 sig figs. So final answer should have 2 sig figs. Now, this is a little more difficult than the other ones because we have given and we want to find the number. So we have grams of diphosphorus pentaoxide. So 150.0 grams of P2O5. Whenever you have anything such as grams and you need to get something else such as number, you have to convert that to moles. So 1 mole, and in this case, you're dividing it by molar mass. So P2O5, if you look at the periodic table, phosphorus was 30.97, 30.97, and then essentially 5 oxygen, which weigh 16.00, that's going to be 80.00. Because there's 5 oxygen, 5 times 16 is 80. So let's add those up. 30.97. You get 141.94 grams. So if I were to solve this, I have moles. Now we have to calculate number. So we have to get to number of molecules. There is 6.022 times 10 to the 23rd molecules in 1 mole. Which, if you're confused at this point, go back to the molar map. To go from grams to moles, you divide by molar mass. To go from moles to number, you multiply by Avogadro's number, 6.022 times 10 to the 23rd. Lastly, it asks for number of oxygen atoms. Every molecule of diphosphorus pentaoxide has 5 oxygens in it per 1 molecule. That cancels out, and then we'll multiply by 5. So the final answer here is going to have 4 sig figs, because we have 4 here, and we also used 6.022 times 10 to the 23rd. If you're to use 6.02 times 10 to the 23rd, your final answer would just have 3 sig figs. Keep in mind here, I will not put on this last Alex of interconverting number of atoms and mass of the compound. We'll do something similar this week before Thursday's test, but there's just better ways to state it. So, all right, so that is week 2 notes. I think reviewing scientific notation and engineering notation is important, and then being able to use that molar map. So you won't be given the molar map on the test. So you have to either fully understand how to do those calculations or be able to write the molar map yourself.